Bismillah ar-Rahman ar-Rahim. Today, let us discuss about what is hypothesis, what do you mean by a research question, how are they related to each other, and we will discuss how to provide evidence. Research is all about evidence, mainly about evidence. When you do something, you have to give evidence, you have to give proof. Why you have to give evidence? The person who is reading your paper is somebody skeptical about your research. The reviewer is skeptical. Reviewer is thinking, okay, he is claiming something. Maybe you will claim something too big, but your experiment is too small to justify your claim. So, this is a combination. Hypothesis, question, evidence. So, this comes from chapter 4 of Writing for Computer Science by Justin Jobel. Here are some few quotes. Normally, we don't go into the quotes, but just for the purpose of quotes, I'm just putting here. Whenever you are giving a statement, meaning an hypothesis, this is a statement that can be proven true or it can be false. But how you prove them, how you discuss about it, it's an intellectual process. Something should be flow, something which should be proper. And people can also contradict your result. Okay? Contradiction is allowed, it is possible. How? We will see. So in any research, you have some question for which I want to find answer. Something, I think, oh, how this will work, how that will work. This is my concern. How to get to a question? How you get question? First of all, maybe you listen to some lecture, you see something outside, you discuss with your friend, okay, you attend some seminar, you got some idea from some course, like this. This is where you get some question. Okay? What is hypothesis? Hypothesis is kind of belief. I am believing using this algorithm is going to improve the performance of the system. It's going to make it faster, for example. This is my belief. This is what I am believing. I don't know. I'm not sure. But this is what I'm thinking. Here is an example. We examine the limits of speech recognition, ask whether web search can be used effectively by children, or predict how well the service will respond to increasing load. Okay? So these are things I'm thinking, whether web search can be used effectively by children, or we are checking for limitations of the speech recognition algorithm, or whether something can increase the load, and so on. So what do? Initially, we speculate, we believe, we say, okay, this algorithm will reduce the computation cost. Then you do some preliminary experiment, preliminary investigation. You check basically. Then you will conduct appropriate experimentation. Please, the important thing is appropriate, not just experimentation. You should do some experiment which is appropriate to your hypothesis so that you can provide some evidence. Note that hypothesis or a research question should be precise, should be very specific, and it should be unambiguous. This is very important. These three should be there. Specific, precise, unambiguous. Okay? So, yeah, ambiguous means something very unclear, not clear. Unambiguous means should be clear. No confusion there. Okay? So, by this, you come up with, you can have a conclusion. Okay? Hypothesis basically limits your conclusion. Meaning, I do this, the system performs better only when this happens. On some condition. Okay? So, condition is allowed in hypothesis. Basically, you should have conditions in hypothesis. Mostly you will have. Okay? Here is an example. Suppose P-list, this is a list technique, or a well-known data structure used for some range of applications, in particular in-memory search structure that is fast and compact. A scientist has developed a new structure called Q-list. So there's already P-list, scientists come up with Q-list. Yeah. Formal analysis has shown the two structures of the same asymptotic complex array. So he is saying some mathematical analysis, formal analysis, comparing P-list and Q-list. He is saying both are similar in terms of space, in terms of time. But the scientist thinks that Q list is superior to P list. What he designed is better than P list. So to do this, he has to give some experiment. He has to do some experiment and he has to define or check it out, demonstrate it. Well, when I come up with an idea, is it correct all the time? No. It's just thinking. Idea comes, just thinking. Everybody has ideas. Then I will think whether it is feasible or not, whether it is worth going into that idea or not. Okay? This all has to be taken next step. So now question goes into the same point. Q list, P list. Q list are superior to P list. Can an hypothesis be like this? Can I write hypothesis like this? If I write it like this, it is very general. So Q list should always be better than P list, which is not true. Some cases it is true, some cases it is not. Yeah, sometime maybe. Okay, the Q list is not good as P list. It is possible. Okay, there is one point to note here. If I say Q list are superior to P list, how I provide evidence? I need to provide evidence for every scenario and prove that Q list is better than P list, which is not possible. Which is not something feasible either. So you have to say on which condition Q list is better than P list. So next line you can see. As an in-memory search structure for large data sets, Q list is faster and more compact than P list. So here he is saying, I'm going to do some kind of memory searching. In that way, it is better for large data sets, not for small data sets. So I'm making some conditions. Okay. So you have to have what is called qualification statement. Qualification statement gives you a scope. It is applicable only in this area, not in everything. Okay, a scope. So it is very important. Some people think, oh, if I put a scope, if I put a constraint, limitation, is my hypothesis inferior? Is it something not good by putting constraint, condition, limitation? No, it's not like this. Hypothesis is generally precisely made like this. This is why hypothesis is precise. Because I put condition. I'm saying only in this situation. Okay? So this is why hypothesis is something that is supposed to be precise. Now a next question comes. Can I falsify hypothesis? Meaning, can I prove the hypothesis as wrong? Yes, you can. If you have an hypothesis, can never be proven wrong, then this is not an hypothesis. You should be able to prove true or false. Okay? So like for example, if I say Q list performance is comparable to P list performance, how I justify this? Comparable means what is comparable? I might think something is comparable. For you, maybe something else. Okay, don't use ambiguous words. Our proposed query language is easy to learn, relatively easy. So maybe it is easy for you, but not easy for the reader. Right? So never make statements like this. Okay? Don't keep your hypothesis like this. This means you are just claiming something for which you cannot prove. You cannot justify. It is not precise. It is ambiguous. Ambiguous is not allowed. For example, if you say I'm using a black box algorithm. Okay? What is black box? Something I don't know what is inside. I have no idea. I don't know the clear picture. That is called black box. Means you have purely understood the problem. I mean, your algorithm is not understood by yourself. How can you prove to me? Okay? So, for example, any research I do, I have some experiments. Please note, experiments are not something that you say, okay, it works for this specific data. Okay? So, results should be general, meaning I should be able to apply for future data, another data, to see how things work. Some people have this habit of using some new terminology. Instead of calling network cache, they call local storage agent. Don't confuse people. Don't confuse the reader with this kind of fancy terminology. Don't do that. Make it clear. Okay? How to write, how to make your style nice, we'll study in the later chapters. Okay? Then, if you have a problem, you should be as specific as possible. Here is an example. a paper on natural language processing for web documents. Okay, if you are talking about natural language processing for web documents, it is about web stuff, not just about text. Be specific. Okay, and sometimes you come up with initial hypothesis, then you do some experiments, some basic preliminary experiments, then you might adjust your hypothesis. But keep in mind, don't change the hypothesis because of your result. Yeah. Don't change your hypothesis just to satisfy your result. No.
Still, my hypothesis is the result is wrong, true or false.
Yeah, and maybe you might adjust it. You might change it a little bit, but not to just change it like that. Okay. So there are some theories which are considered to be true always. Okay. Unless proven wrong. This is the word they have assumed. Okay. They have come up with an assumption. Unless it is proven wrong, something is true. Okay. Like under the theory of general relativity. We are not going into that topic. And please note, you cannot write statements like this in your paper. An algorithm worked on our data. So meaning, whatever you did worked only on your data. Okay. Or you are saying things worked on any class of any data of this class. So you are specifically saying it's working on this class of data. So what about others? What is the situation about others? Okay. So you start with a hypothesis. You test your hypothesis. Don't just, like for example, I have a hypothesis. Just because I want to satisfy the hypothesis, I fine tune my experiment. I change my experiment slowly, change some number here, number there, to make sure my hypothesis becomes true. Not like this. This is like you are fooling things around. Okay. So if suppose I can write something as two types of hypothesis, two hypotheses, choose the one that is simple, that is precise, that is unambiguous, that is specific. Be clear. Okay. So defining an hypothesis is very important. There is something which is equally important. That is providing evidence. Okay. So for example, if somebody says a new range searching algorithm or method is faster than previous method. So this is his statement, his hypothesis. Can be true, can be false. I should come up with evidence. Evidence comes from experimentation. Okay. And then from the experimentation, he says it takes so much time while the other one takes so much time. We can compare now and say this is faster. Okay. So evidence should be in sync with your hypothesis. Evidence is testing, yeah. Right? So writing hypothesis is like you are defending your hypothesis. What is hypothesis writing? Basically, like I tell you something, and you start questioning me as a friend. You say, oh, why you like this? How like this? People question you, right? And you are trying to defend. You are trying to explain your view. For example, if I start saying to you, you as my friend, the new string hashing algorithm is fast because it does not use multiplication or division. I say this. Okay, it's fast. I'm claiming mine is fast because of these reasons. There is no multiplication, there is no division, whatever. Then you ask me back, what is the problem with multiplication, division? Okay, what is the issue? There is no problem. Then I explain to you back, look, instead of doing this, I'm doing this. I'm using some approach which can be done as pipeline approach, can be something parallel. I'm explaining. Then you are asking me, and I said to you, okay, I'm using approach which use modulo approach, modulo method. Then you ask me, yes, modulo is also not easy on a hardware. It consumes a lot of power. Then I tell you, yes, it is true, you're right, but I'm using this only once in my algorithm, only one time. Then there is another question, right? Look, you are asking me, there is also a lookup. You are going to look for something in an array. Looking in an array is slow. It has to go to the element and look around. Then I'm saying, no. Array lookup is there, but I'm using cache residence. Something which is brought to the cache so it becomes faster. Well, then you are asking me a question. What if your hash table is of not this size, 2 power 8 or something specific? then I'm saying yes, it is good. I did try with 2 power 8, 2 power 16 and so on, it is working fine. So it is like you are defending something. Okay? Always when you write your hypothesis, when you write in your paper, in your report, in your thesis, whatever, you also have to say, look, it's hypothesis. I have this thinking, this hypothesis. When I thought over the hypothesis, I had this objection. I have these queries with me and I have answers for them. You should provide reasons, okay, why I'm using this, right? So if suppose there is some objection which you cannot refute. For example, I said the hash algorithm. You ask me a question about multiplication division, and if I cannot answer, for example, if I get stuck, that means I have to go and change my hypothesis. I need to change something there because I am not able to convince you, you as a reader, you as a listener to my hypothesis.
We expect the answer in the experiment.
No, normally, hypothesis can be proven as true or false based on experiment. This experiment, we call it as evidence. No, even it is true or false, it is hypothesis. Hypothesis is still a hypothesis.
Something that we can test.
Yeah, that's right. And what if your hypothesis is against your common belief? Okay? Let's say there is something that you think and your hypothesis is, against it. You think this is the normal thing, but does not happen. Well, verify whether all observations or scenarios in the common belief were considered or not. You have to check everything on your hypothesis. Verify that. That's all. When you start writing hypothesis, be skeptical initially. No problem. Be skeptical. Be doubtful because you don't know the answer. You are only assuming. You are only guessing. Later on, after doing some experiment, you can say, oh, okay, my experiment is going good. Everything is going good. So hypothesis stands as it is. No big problem. But if you have to take ages, okay, years to prove your hypothesis, then it's a waste of time. You are not doing something right. Maybe your hypothesis is too vague that you cannot prove it until now. Prove it right or wrong, doesn't matter. But if you are not able to prove for years, then you are wasting your time. Your hypothesis is so vague that you cannot come to an answer. It should be precise, it should be unambiguous, it should be very specific as well. Well, if suppose I have a feeling my hypothesis is very strong, then I should do my experiment also very strong. I should try rigorously, strong checking, because I want to validate, okay? So what is the next step is convince the reader. You have to make sure the reader will believe you. Reader means the reader, reviewer, anybody, okay? Anybody. So suppose you come up with an algorithm to solve a problem. First question, the reviewer will think or the reader will think, is your algorithm new or not? How to prove it is new or not? By having a good literature review and show them, look, this is what people have done, I'm doing this, how is this different from that guy? From the old one, this is different. This is number one. Number two, will the reader believe your algorithm is good enough? Okay? Then you have to come up with proper explanation, you have to say what are the problems, how does it solve? Is your experiment convincing? Maybe you can provide the code online, maybe you can provide the data set, you can make things public, or you can use a standard data set. This is possible. So, how to do evidence? We have seen what is hypothesis. Now we are going to see about evidence. What are the types of evidence? In any paper you write, you read, you should have evidence. Okay? And you should have explanation about the evidence. If you don't have evidence, then it is not good science. It is something you are just making stories around. No use. Evidence should convince the reader. The reader can be something critical about your work, somebody critical, somebody who is skeptical as well. It's possible. Okay? A reviewer will check the paper in a skeptical mode. This is normal. Nothing wrong. So how to prove them? There are many ways. You can go with the proof, you can go with the modeling, you can go with simulation, you can go with experiment. So let's see what are these four, how are they different to each other, what to use when. Okay? Proof is like formal proof, mathematically proving that things are true or false. Please note that proof can also contain some errors. It is possible. Proof that if you prove something doesn't mean it is 100% perfect. No, there is possibility of some error as well. Sometimes proof is not at all enough. It's not sufficient. Why? Suppose I'm saying I have an algorithm. It does what is called compression of images, lossless compression, and it is very good. It's faster. It is efficient compared to old algorithm. Your proof might not be enough. People want to see it in an experiment, for example. Okay, then you can go for second one is model. Here again you have mathematical description of your hypothesis. This is modeling around. Okay, so you model your hypothesis, right? And then you can test it as well. You can test it like modeling the cost of a Boolean query on a text collection. You have some data collection, text file. You want to do some query. What is the cost of it? What are the tasks involved? Number one, you want to find documents that contain each of a set of words. I have some words, I'm searching for that word in those texts. This is number one. Number two, how I consider whether a document has a word. If it contains a word only one time, I don't give priority. If it contains 10 times, frequency of the word. Okay? So if something appears heavily in the text file, or maybe if you are searching for a file, the file is again searched many times, means it is in the cache, for example. Okay? You are putting it in the cache, so it becomes faster. Right? Sometimes it becomes very difficult. If you have many parameters, and you want to model it, it will be tough. Third approach is simulation. Simulation, you do implementation. It might be full implementation, it might be part of the implementation. What is the difference between simulation and experiment? Simulation, you can say, okay, I will approximate this. There is no noise in the system. There is no other traffic. Only this traffic is going on. I can make some approximation. I can make some omissions. Okay? And simulation is a white coat test. White coats meaning artificial. It is isolated from the real network, real situation. I conduct it in my lab, in my laptop, for example. Okay? Nobody else has any impact on it. Right? Advantage of simulation, I can change the parameter easily. I want to change from 10 user to 20 user just by one click, change. Easy now. Okay? But the limitation, it is simple and it is not realistic. This is the problem with simulation. Well, we find many papers they use simulation because experimentation is not easier as well. Next one is experimentation. Experiment, you work on a real data. It's on real data. Right? The difference between experiment and simulation is this. Experiment, you are really doing it. Simulation, you are like pretending to do the real experiment. You are just pretending. Okay? So, there is a limitation in experimentation. Why? Experiment, I experiment on a specific data set, specific situation. What about other situations? Is my hypothesis true or not? I did not check it. I did not test it. Because my experimentation was done in a specific environment. This is a problem with experimentation. Okay?
Is it a weak point in the paper?
It's not everything has plus minus. Okay? All four of them have pros and cons.
I can suggest to the future review.
No, what they normally do in a good paper, they will have combination. They will have both, not one. You will see they will have formal analysis with experimentation or formal with simulation. Like it is, they have a combination. So this will take the plus minus from both sides and somehow balance. It's not perfect, but it will balance things down. Okay? So you conduct experiments based on this. When you do experiments, you try to keep also some extreme ones. You have to check for extreme data to check whether it's okay. So you can validate something using different evidences. Let's say I am having a question like this. If some proposed algorithm, for some proposed algorithm, a mathematical model is defined. If this model is just implemented and performance is predicted, is this an experiment or not? So what do? You have some problem, you mathematically model it using some variables and things like this. Then you implement that model, not the actual experiment. You are doing the model. So is this same as experiment? No. Experiment different. This is modeling is implemented, which people do as well. They create model, they implement the model, and they get the results from the model. Okay, this is possible. So question is, which evidence to choose? Like you were asking few minutes ago, which one to choose? Simply don't choose that is easy to do. Choose something that is convincing to the reader. It can be easy, no problem, but it should convince the reader. Whomever is going to read should get convinced what you are doing is right, what is appropriate for the hypothesis or not. Right, never do experiment in the last minute, never. From the start, when you start your thesis, when you start your proposal, start thinking, what evidence I'm going to provide for this? Because if you don't think about the evidence, you'll just come up with some funny hypothesis, something which is ambiguous in nature by itself. Okay, this is a problem. When you read something, normally you have to provide literature review and you reference to some papers. Please refer to standard papers. We have already discussed this one, right? You have to take published good quality papers as your reference, both in experiment comparison, result comparison, also in literature review, everywhere, okay? And there is a statement they make, anything that is published, okay, they could be false. Possible they are wrong in some sense. But anything which is not published is the worst. It's something beyond that, okay? So this is some statements they make. And how do you measure things like? Okay, in terms of measurement can be of two types. Qualitative, quantitative. Okay? So it can be of two types. Why you need measurement? Measurement gives you the evidence. Without measurement, I cannot prove the evidence. I cannot prove my hypothesis. So measurement is logical. I have to do it. So measurement can be quantitative, which is in terms of number, some volume, some number values, okay, like speed, like this, or can be qualitative and quantitative. Quantitative in terms of number. If you take qualitative, okay, you can say whether this one occurred or not, whether this is achieved or not, whether the person was able to, security block was there or security permitted, deny permission, like this, okay. So, from the research question or the hypothesis, you have to say what I should measure. What am I going to measure? How am I going to measure these things? I will have to think, is it good if I just measure the execution time? Is it enough? Or should I measure something more? If I have to measure execution time, how am I going to measure it? Okay, how? Why how? Because there are certain things which can impact your measurement. You have to consider all this when you do your measurement, okay? So, your measurement should match your aim of the research. Normally, your aims are qualitative. Normally, aims are qualitative. Like you will say, I want to accelerate the algorithm. I want to improve the algorithm, okay? I want to extract good information from the big data set, right? I want to put something which is more qualitative kind of. This is my aim, okay? But when you come to the measurements, it becomes quantitative, right? Then I will say, I'm going to compare this approach with that approach. How much I am comparable? I mean, how much? By what value you are okay, not okay? You have to come up with some numbers. It becomes quantitative. A network, for example, it's about round trip time. Data go from the requester, client, for example, go to the server, come back. This is called round trip time. Is this enough? Maybe not. Not just round trip time. Maybe effectiveness of the video. If I am streaming, round trip time is important, but at the same time, smoothness of the video is also important. If the video is, it has a lot of detail. If it is not good enough, I cannot watch the video. No use. Okay? So, a qualitative aim is approximated with many quantitative measurements. Don't consider I do only one measurement and everything is tamam. No, not complete. You have to take some kind of measurements which you do in terms of quantitative and then map it to your aim. But remember, I did discuss a point here. I did not discuss with you, but I have discussed with some others. You have hypothesis. You have methodology. Okay? You should map your methodology to the hypothesis by saying, hypothesis 1 is taken care of by methodology number 1, number 2, number 3. No problem. One hypothesis mapping to many methodologies. Why? I have one single statement. To prove this, I need these measurements to provide them as evidence. Okay? This could be possible. Sometimes if you use a standard data set, depends on the data set. If the data set contains everything in one single format, one single structure, style, then you are only proving your research based on that data set. What about others? Okay? Does the data set contain ambiguous things or not? Okay, let's move on to what is called good science, bad science. We are learning this so that we don't do bad science. That is the point. It's very easy to say this is good research, this is useless research, or pointless research, or weak research. Okay? So, answering back the question, you can combine formal approach with experimental to come up with a good research evidence. You are giving evidence from two sides, not one. Okay? So, you can put things together. Sometimes people come up with just theory only. No, theory alone is not sufficient. Practice alone is not sufficient. You should be able to combine them. Okay? You should be able to prove something theoretically as well as using some practical approach. And don't come up with over-inflated terminology. Unfortunately, some people use the word hypernet. What is hypernet? Is it network or not? If it is network, why are you saying hypernet? Okay? And if we use the word, for example, intelligent approach. Okay? I'm using an intelligent system. And I say, I believe it will work very fine. It's working very good. I'm aware of this. These words you are making mean something to you, mean something else to me. Reader understands it differently than you mean it. So don't use this kind of ambiguous words. Okay? So there is a list of these words which you should avoid, which you will study in a later chapter. I think chapter 6 or something, you will discuss that here. Right. For example, if somebody says a text indexing technique that maps terms to concepts about semantic retrieval. This is his statement, okay? People can understand differently. Are you just using a dictionary and mapping things or what? What do you mean by semantic retrieval? Are you using ontology? What are you doing? Be clear. Don't just use one word and hide your actual work. Okay? So, some people say in their result, we did experiment 100% accurate. We tried to map data between some text. We got 20,000 match, 10,000 match, like this. When you say this kind of round number, already people start doubting. They will start doubting your experiment. 100% accuracy, so there was no error. So meaning you did not do proper testing maybe. Experimentation is not complete. How you match 20,000, exact number, not 19,644? 20,000, perfect. So these things will make doubt in the reader, okay? Don't come up like this, don't do inventing a problem. You create your own problem which never exists, hypothetical problem. Come up with a solution for it, and then you make your own measurements of it. It's all story making, right? We are not doing some story building here. We are doing some research. So if you do story building, that is called bad science. Unfortunately, some have this habit. People come, oh, I have a good idea. Right? Just good idea. Did you verify your idea is okay or not? Did you check what has been done in the literature? Do you have proper evidence to prove your idea? Do you have substantial experimentation or formal analysis or modeling or simulation that you can consider? Okay? Here is a discussion, a nice discussion. You will understand something here. There are two people, two philosophers in a coffee shop. In the book they use some other shop. I just changed it to the word coffee shop to be recent here. Alright? They were arguing between each other, as usual. They were saying whether computer science is a science or not. That was the debate. The guy, who is the coffee shop guy, right, he comes and asks them, look, what are you arguing? Right? Then they said, this is what we are arguing. Okay, this is what we are arguing, and then did you conclude or not? Is there a final decision? The guy said, no, there's no decision yet. Then they are saying, what is your problem? They said, we are arguing what is that if meaning. Computer science is a science. But what is that meaning of that word if? We are arguing that one. So it looks very funny, you know, they discuss about computer science is a science, and the argument goes into that small word if, right? So don't go to this level. This is what they meant. Don't go and beat around the bush or go and do some experiment which doesn't match your hypothesis and make things crazy around, right? So please note that people always read your papers, your articles in a skeptical mode. So prepare to convince them. Your hypothesis can be proven negative. It is possible. Does that mean if your hypothesis is proven false, okay, what do we say? Is that hypothesis wrong? No. What we normally say is this: if your hypothesis is proven wrong, proven false, maybe there is some assumption in your experiment which is wrong. Why don't you change the assumption in the experiment and see what happens? So redesign your experiment. Okay? So you are trying to confirm your theory through some experiments. Okay? And well, if you can never prove your hypothesis wrong, that means your hypothesis is not at all a hypothesis. Something very uninteresting. Here is an example. A search engine can find interesting web pages in response to queries. Obviously, it will always find something, right? Can find. It can find. You cannot prove it as wrong. So this is not an hypothesis. Okay? So don't build hypothesis like this. And contradictions may be due to an incorrect hypothesis. Maybe you come up with a wrong hypothesis. We have seen a lot of not so good hypotheses until now. Okay? You can use them. So in research, you have theory, you have evidence, you have to prove them. Last slide here is a checklist. I'll quickly read the checklist. This will be helpful for you after you write your hypothesis to verify, to check. Exactly from the book I copied it here. This is verbatim from the book. What phenomena or properties are being investigated? What are you investigating? Is it interesting to the people or not? Why is this interesting to the people? Okay. Are you having an aim of the research and is it articulated properly? Is your hypothesis, is your question specific or not? Are there elements which are connected properly or they are just isolated elements? Is your aim or a claim innovative? Is it novel? Is it something original by you? Can you disprove your hypothesis? What are your assumptions? Is the assumption reasonable, sensible enough to use it? And did you really question your own hypothesis, your own work? Did you question yourself so you can come up with some discussion on that line? Do you have some evidence? Do you have some simulation, modeling? What? In any scenario, do you have theoretical validity? You have practical validity? Okay? Is your measurement appropriate, reasonable to the respective hypothesis or not? It is clear or not? What are your qualitative aims? What are your quantitative measurements? How are they matching with each other? Okay? And do you make any approximation, simplification in your experiment, some kind of changes you made? Does it affect your outcome? Okay, do you have some proper arguments to link your evidence to the hypothesis? You have to say, okay, I do this experiment. By doing this, I'm mapping my hypothesis. I cannot just write experiment separate, hypothesis separate. This is normal in some of the weak papers. They write the hypothesis separately. They write the experiment separately. Fine, but there is no link. They are not linked. You should have a link between them. Okay? So how you prove your hypothesis, how you disprove, are there any weakness or limitation? Some of us again think that we should have no weakness, no limitation. Research is not about just hiding everything. It's about telling, this is my limitation, these are my weakness, this could be the future work. I will stop this lecture with the one last point. There is a difference between a project and research. What is the main difference here? In project, you want to do the think and complete. They ask you, okay, build something, you build it. In research, it's not about building it completely. It is about checking whether it is efficient, whether it is good, how good it is. Is it worth to do this in this line? Okay, you go and prove. You go and do some measurements. In project, no measurement needed. As long as these are the requirements. Okay, requirement 1, 2, 3, 4, 5, done. Halas, project finished. Is it taking 1 minute to do the job? Is it taking 2 minutes to do the job? Not their problem. As long as user doesn't feel it to be very slow. If it take 1 second, 2 seconds, 3 seconds, user don't know. It is okay for him or her, right? But when it comes to research, this second matter. Okay. With that, we complete this lecture. Let me just disable recording here.